Okay, so let's start the first hands-on session. Having theoretical knowledge is good, but to really work with actual data is a completely different ballgame. And to have someone who's an expert on this is a rare opportunity that we get in India, at least. So make complete use of Shadab over here and sort of go through whatever he teaches and catch hold of him because he is always around. And really pester him to know things that you will actually use in your research. Shadab.
Hello, everyone. Thanks, Subha, Rishi, and everyone, all the organizing committee for giving me this chance to introduce some of the large-scale structure analysis tools. And this is going to be, intended to be a very interactive session, so all of you are actually going to do analysis. Today we are going to do something very basic, but to start with, all of you are on Slack now, right? Is anyone not on Slack? Please raise your hand. Okay, so I take it as yes. I just sent a link to a JetLab repository. I hope all of you have opened it. If you scroll down, you should be able to see this link. If you just click on that, can everyone open that link? Just click on that, it should open a Jupyter hub, which should look something like this. It might take a while, so just let it open. Once you open that, you should click on tutorial, and then on tutorial 1. You should get something like this. So it might be like just loading up, which is fine. Meanwhile, I will speak a few things and tell you how to set up everything. So if you're not familiar with Jupyter Notebook or Python, it's not a problem. I'm going to tell you basically the basic things which you're going to use here. So let's start with a little bit of what's the idea here. We are going to try to, I'm going to try to show you like how to also intuitively understand correlation function. So in today's session, we are not going to use anything related to cosmology, but very simple sort of model and try to understand what does pair count mean, all the things you have been hearing, two-point function, what does it mean in practice, and what can you understand in terms of like the structure of the field or the structure of whatever things you're looking at. Okay. Yeah, that will be great. So tomorrow, Aseem will cover a lot of theory, and I'm not going to cover actually any of the theory, but I will try to give you the big picture essentially in the beginning. There are basically three separate things you can think about. And this, for people who are not familiar with Python and Jupyter, you'll get familiar during the session by working out things here. We will understand general idea of correlation function, and at the end, we will try to do some cosmology-specific analysis. So it's not going to be the session where I'm going to teach and you're going to learn, but all of us should try to teach each other. So people who know Python will be able to complete the exercises much faster, so you should try to help your neighbor. Anyone who have difficulties or not able to solve should come to Slack and ask a question. For example, you can say whatever your question is. So a little bit about Slack, you can take a screenshot, you can take a plot and send it here. So you can send anything. And if you're interacting with someone on a particular topic, on a particular question, then you should try to use something called threading essentially. So you reply to a message in place of replying to the whole thing. So if you go to any message, it will show you this little message icon. If you click on that, it opens a thread, and then you can say, I can help, and then try to help whatever question you think you can answer if you have already solved the problem. Right? So that's how we are going to do it. When you use thread, it will help the whole message board so that we don't have a lot of like many different things and many different people trying to answer many different questions at the same time. So it will separate out conversations a little bit. So this is how we are going to use Slack. Now, for everyone, did it open? Jupyter Notebook open? Anyone having trouble with that? Okay. Sorry? Wi-Fi is slow. So for how many people it didn't open? Can you raise your hand? Oh, wow. There's a lot of... Did you get this screen? The first screen? Okay, so let's try to use the other thing. So for people who could open the thing, can you see the Jupyter notebook which I was showing, right? All right. So for whoever could not open, if you have a terminal in your computer, can you open a terminal? It's very quickly. I'll guide you through two steps with which you should be able to connect to another system. So if you open the terminal and just type this command, which I'm going to send on the Slack again, and press enter, it should ask you for a password. And the password is... So this is all internal network, so it should not be so much dependent on the internet. I hope it will work for all of you, whoever could not connect. And once you have done that, and you have typed the password, open this link in your browser. So let's try this. This is the first step, which if we solve it, then we will achieve a lot of things today. Sorry? Oh, you should see your own Slack. This is just I'm trying to guide you through, but all of you should have Slack on your computer open, right? So all the messages should be coming there. Don't try to type the command, just copy it and paste it on your terminal. Okay, so please keep trying, and I will ask again if for some people it didn't work. So let's just briefly go through the big picture. So you have listened to several lectures, right? Starting from the inflation, a lot of things you have heard about the CMB, and from CMB, we know how the initial universe looks like, how the baby universe looks like, right? That's what we measure by looking at the CMB power spectrum and everything. And that gives a pretty good understanding of what is the constituent of the universe. And then on top of that, we have this model of the universe, which is called Lambda CDM, and which is based on, which assumes GR as the model of gravity. So if you have this initial condition and you have equation of motion for the whole dynamical system, you can evolve your universe to the current age. And you can ask the question, what kind of a structure will form and what sort of galaxy should be there? And once you have this structure, you can try to look at the statistical properties of this system. So what we want to study is essentially look at these galaxies by doing surveys, cosmological surveys, and look at the statistical property of these galaxies to understand if we understand the initial condition, if we understand the equation of motion, then do we get the right thing? If not, then there must be something wrong either with the model we assumed or with the initial condition we understand. But if everything fits together, then Lambda CDM basically explain our universe. So that's the rough idea, which you'll hear in a lot more detail. So let me ask again, anyone still doesn't have Jupyter Notebook on their screen up? 1, 2, 3, 4. So you tried doing SSH and still it didn't work? At what stage did it fail? Sorry, Slack is not opening. Oh, even Slack is not opening. This I didn't expect, the internet will be so slow. But whoever is connected should not try to change anything if you're already connected, so that you don't spoil. So how many people can I see that again? How many people cannot connect to even Slack? So like the internet is not working for you essentially. Sorry? Oh, so for your notebook is there, but Slack is not connecting because the internet is weak. Okay, so probably we'll have to figure out something in the next session. What is the alternative for having weak internet? But let's go ahead a little bit while we give the internet a little bit time. So all of this is going to be on Jupyter Notebook. What is Jupyter Notebook? It's something very similar to Mathematica Notebook, if you're familiar with. So it's a setup which you can install several kind of softwares, and you can make notes. So there are two kind of things. You can make notes like this kind of things, and you can write code and execute code. And Jupyter can be used with several languages. Like, in fact, Jupyter stands for Julia, Python, and R. But other than those three languages, there are of the order of 40 languages you can set it up with. So this Jupyter Notebook is all set up with Python. There are a lot of details. I've kind of described basic properties which you can read later. But remember, the key thing in Jupyter Notebook, to execute any cell, you have to press Shift-Enter. So whenever I will ask you to execute a cell, remember to press Shift-Enter. So that's how you execute any cell. Now let's move to Python. So people who are not familiar with Python, Python is a very powerful tool. You should get used to it. There is some description about it. The main thing about Python which you need to know for this session is it follows indentation, which means in other programming languages like C++, you use curly brackets to open and close blocks. But in Python, the number of space you give to is what decides. The indentation decides when a block is opening and closing, which you'll see example of as we move on. So remember, whenever there's an error and things are not working, you should first look at indentation. Is your indentation right? The next thing is, again, very quickly, for Python, there are a lot of libraries available which already have a lot of functionality. And all you need to do is to load these libraries before you can use it. And to load any library in Python, you just have to say import, name of the library, as, and some keyword which you want to call. Like basically you rename the library with something which is alias. The two main libraries we will be using is called Numpy and Pylab. Numpy is a numerical package library which has a lot of numerical algebra functionality. And Pylab is what we will be using for plotting. So for whoever have access to Jupyter Notebook, can you execute the first cell, which is importing the two library? So press Shift-Enter, select the cell, press Shift-Enter. And that should just load the library for you. So let's see how many people still cannot access Jupyter Notebook, even after giving this much time to internet. Can you please raise your hand one last time? 1, 2, 3, 1, 2, 3, 4. Okay, everyone else can access Jupyter Notebook. So can I request you to work with your neighbor for the time being? We'll try to figure out in the next session how to do it. Like if you're sitting alone, please sit with somebody else and work with them. Sorry about this limitation. So the next thing I wanted to point out very quickly in the Python introduction, there are several functions, and if you don't know what the function do or what the function signature is, you can ask for help. So you can just say, for example, this is a numpy function linspace, which creates linearly spaced array. Let's say I don't know its signature. I will just say np.linspace, question mark, and press enter. That should open up a help for you. So are the cells working when you're executing it? Did it work for anyone? It worked, okay. And so for most people, it's not working, is it? Okay, so people who connected through SSH, I forgot to tell you one thing. People who connected through SSH, can you raise your hand, whoever were able to connect through SSH, the SSH command? Okay, so when you open the Jupyter notebook, did you went to the tutorial folder? Yeah, so sorry, I forgot to tell you, in there you see your username should be there. Before going to tutorial folder, if you come up, you should find your own username, which is the name you used for your email. Go to your folder and then open the Jupyter notebook and then execute. So are the cells executing or you are getting any error? It's executing, right? So I can move ahead. Is it not executing for several people? It's not executing for you, Mayor? Okay, so it's slow. Yeah, sorry, I did not expect internet to be too slow. So slow. So it doesn't look like. Yeah, but it's like just browsing the net. Okay. So I guess, yeah, then we'll have to install things on individual system, which we'll do. Right. So I can, yeah, I guess we can try to install things. So in this case, we will not be able to kind of work things together, but I can probably just run you through what the things are. And I was hoping you to try, but looks like it's not going to work out with this internet. Right. Yeah, that could work. So should we ask people to make groups around wherever there's... No, it doesn't require any installation. So that's another local server, but it doesn't require outside network. So you can use SSH as well if you are able to connect it. It's really the internet which is the limitation there. Yeah, even I can't see that cells are executing. So for people who connected through SSH, the cells are executing for you? It's executing for you? It's executing? Okay. So maybe more people can switch to SSH because that's a local network. So that won't need internet. It should be over LAN once you connect it to the Wi-Fi. You'll need a few more things. So no, not just Jupyter. You need like some packages, cosmology specific packages as well. Can I ask everyone to switch to SSH? Like for whoever it's not working, it's not executing. So you know how to do it. You open a terminal, type the command which I sent on the Slack, and type the password. Then you go to the link. Then you go to this link and open your username and your tutorial. Okay. So let me introduce a like really basic Numpy array and Python plotting for now. So there's this function which is called linspace. It essentially creates a linearly spaced array in Python. All you have to do, if you could pull up help, you'll be able to see that. You have to say the starting point, ending point, and number of points. So that's what I have is 0, 2 pi, and 100. And then you can, any trigonometric function, all of that is available in NumPy. So you can just say, for example, numpy.sine xx. Xx is the array of angle. So y will be sine of x. Now, in order to make plots, all you have to do is just call pl.plot what you want to have on x-axis, what you want to have on y-axis, and just press enter. And then there are more details about how to label the plot and things like that, which you can ignore for now. So you'll create a plot like that, which is x comma y of sine x. So if you understand this much Python, you should be able to work through most of the example later on. There's one last thing before we start looking at the correlation function, is about the slicing NumPy array, right? So the NumPy array could be of any dimension. It could be 1 dimension, 2 dimension, 3 dimension. The first thing you can do is, if you want to, let's say, figure out what is the size of the array, you type your array.shape. That will print the size of the array. You can slice any row. So the symbol colon used here says basically everything, and you can select any column by just giving an integer number of the column. Or you can select any row by again giving the integer row and then colon to select any row. So you can essentially type any combination of numbers there to extract a subpart of array, which is what is shown here in this thing. Okay, so let me check again. How many of you are able to now connect with SSH and Jupyter Notebook is working? Where working? So you have working Jupyter Notebook. It's working on? Normal. Do you have working Jupyter Notebook? Can you raise hand if you have working Jupyter Notebook? Okay, so most of you have. So whoever not have, can you just pair with your neighbor and just try to check if try to execute the cells up to what I've discussed with slicing, and if it's executing or not. You're not getting the... So you're not getting the print. Oh, this is the sin x. You're not getting this plot. Did you execute the first cell when I asked you to, the top cell in the beginning? Can you go up and execute the top cell? Like basically press shift enter and again execute the cell which is to make the plot? Let me see. Yeah, it seems to be working really smoothly on SSH. So for whoever has the notebook open, are you able to execute up to this point till the array slicing? Okay, so now let's move to the 2-point correlation function, which is what we want to first measure, the idea of it, right? So let's say you have a field and you have points in the field. And what you want to ask, the way 2-point function is defined is that if you look at pair of points in the field and count how many of them, then what is the excess probability of finding a pair of points compared to random distribution? So if your points are distributed randomly, then what is the excess probability of finding a pair of points in your field? I know this is a little bit vague right now, but we will actually work out through this to figure out how it looks like. So in this cartoon picture, I have like pair of galaxy. I can measure the distance between them, and I can do it for all of my galaxy in the sample. and figure out and just count how many galaxies I have as a function of distance, this will give me correlation function, which looks something like that. All right, so this is our target, which you should measure at the end of the day. Now, if you move, I've written a function. So any function I will show you, all you need to see like what is its signature and what it does. You don't need to understand the detailed code of it, right? In the first place. So if you're able to understand the signature and if you're able to use it, that should be fine. So for this cell, the first thing you should do is execute the cell. And let's see. So what this does is there's a function called create data in cube. So all it does is it create data points, however many number of data points you want in a cube, right? And all you need to say is the NPT, which is the number of points per site. So let's say if I say NPT equals to 5, it will create 5 cube points, which is 125. You can ignore everything else for now. The next detail is, if let's say I want to put 125 points in a cube, how do I want to put it? What should be the structure of the point? So that is the option you can decide using this structure. So the structure could be either grid, which means you put the points in a cubic grid, or you can say random, which means you distribute the points randomly, right? So this is all this function do, and it returns a Numpy array with x, y, z coordinate of the points it has created. And then we have this function draw unit cube perspective, which basically just makes a plot of it, right? So you don't need to worry again how it works, but as an input, all it takes is a pxyz, which means xyz coordinate, which you created from the first function. And if you just give this, and it takes something called side length, which is the length element of your internal cube you have generated, which will be returned from the previous function. And you can say grid on and off, which is drawing line between nearest point. This is just a functionality, and plots equals to 1. So if you just call this function, it will create a plot, which I will show you how to do it, which is in the next cell, right? So here I'm doing two things. The first thing I'm doing is I'm calling my first function, create data in cube, and I'm saying create cube with a number of points 5. And I'm asking again, it's calling it again with 5 points, but I'm asking it to generate randomly. And then I'm just drawing those two. So this is how it looks like, the plot. You should try to execute this cell and see if you get this plot. So you can see the first plot shows basically a cubic grid, which is what I wanted to generate. First plot shows a random distribution of points, so there's no grid structure. Now, once you have this, these two set of things, let's say if I go back to the idea I told you, which is counting pair of points as a function of distance. If we do this, then what will you find for these two things? Like, do you have expectation? What should it be there? And that's exactly what we are going to do, and that's your first exercise, right? But to be able to do that, now you know how to create these points, but you don't know how to do the pair counting, right? You can write pretty simple functions for it, which I have written for you. And you should again execute this cell. So shift plus enter, press this cell. This is the third function I'm telling you about. It's get pair count. So all it does is calculate pair counts. It takes input as XYZ coordinate in the cube, which is what you generated in the previous step. And then there are several other inputs which you are going to ignore for now, which I'll explain later in the session. So you execute this cell, and this is how you'll get the pair count. And all it returns is essentially 2-column array. The first column is going to be pair separation. The second column is what is your pair count, how many points you found at a particular distance, right? So now you have these two functions, and that brings us to our first exercise. So the first exercise is you create points in a cube using this create data in cube point, and then use this function get pair count to actually compute the pair count, and finally make a plot, which I showed you initially how to make a plot, just XYZ plot for both of this kind of cells. So you create grid points and random points and look at the pair count. I also specify the number of points you have to give, number of points equals to 21. And make a plot to see how it looks like. So I'll give you like few minutes to give it a try. If you get into trouble, either raise hand or write in Slack. Hopefully somebody will respond. So you should not actually see that solution. That was the solution I was showing you. And if you have no idea what the question is, then also write on the Slack. I will respond. So I'll give you a few minutes with this. Okay, so the question, somebody asked me to repeat the question for whoever didn't understand the question. The question is, I want you to create data in a cube, which I showed you how to do it in the previous step. I showed you with 5 points how to create a cube, and I plotted it. So don't make a plot, but create data in a cube using this function, which you just executed on the top, where all you need to say is how many points you want. And I want you to use 21 points. So 21 on the side, you'll create 21 cube points. So create data in a cube for two kind of structure, grid and random, both of them. And then use this get pair count function, which I've just defined the signature of it, to do the pair count, which will count how many pair of points it finds as a function of distance, and finally make a plot of that. So make a plot of R, distance versus pair count. Let's see if you can understand the syntax in the first exercise. So this is how, for those who have difficulties, this is how the solution, like the code will look like. I will not show you the plot yet, but this is how the code will look like, what the code I'm asking you to write. And this is going to be, now in your notebook, this cell is going to be empty. So this is where, in that empty cell, you need to write this code and execute it to see what kind of plot you get. So how many people have done it successfully? Anyone completed it? No one. Looks like it's difficult than I thought. Okay, so can everyone paste the solution I sent on the cell and see how the plot looks like, which will look like something like this. And you can go over the solution in more detail, but if you understand the function signature, it's just a matter of time you understand how it really works. So if I plot as a function of pair separation, then for the grid distribution, I'll get the blue points. And for the random distribution, I'll get the red point. This is how it will look like. Did anyone, I think Sukanya got it. She sent a plot. Did anyone else got it? Meir, Utkarsh. So if you can just paste the solution I sent over Slack now, and you can go over in detail over the solution later on. But this is what it should look like once you manage to get it. So let's try to understand what does it mean. Can we predict this? For example, for the random distribution of points, can we predict what it should be? Can we write a theoretical expression to get this curve? And will that match with our expectation? So this is what I want to do, like just walk you through a very simple description of how will you try to predict something like this. And this is like, this is not so useful in general for the real data, but it's very useful when you're analyzing simulations because it has some assumption. So let's say you have random distribution of a point in a box, right? And all you're asking is at a certain distance, how many pair of points you'll find. So this random distribution of points, if you have n number of points and the box side length is L, the density of points is n over L cube. Okay, so if you look at a certain distance from a point between R1 and R2, which are two distances, so you'll get this shell. Now, how many points are going to be in this shell? So the number of points is going to be in this shell if it's a uniform random distribution is the volume of this shell multiplied by the density, right? So you know the density, the volume of shell is nothing but it's a spherical shell, so it's 4 by 3 pi R2 cube minus R1 cube. So that is the volume of the shell. Now, so the number of points in this shell is going to be number density times volume of the shell. Now, how many of such shell you will be able to create in a space like this? So you can create such a shell around each of these points, so around nr number of points. So if you just multiply n shell by nr number of points, that should be what your pair count look like. So this is what the analytical expression looks like. It has some assumptions, which is you have a uniform random distribution and you have an infinite box or periodic boundary condition. Otherwise, it will fail. So what I wanted you to do the next is, it's a very simple expression. So you can write a code, you can write a function, which will essentially calculate this. And how do you do that? So for Python, to write a function, it's a very simple thing you have already seen several times. So you write essentially def, whatever your function you want to call it, and whatever input you want to give it. So one input I would want is R1, R2, R3, all the bin edges, right? So R bin edge, number of points, and the length of my cube. This is all you need to compute it. And then you just evaluate this expression. So in all of this, I do nothing but evaluate this expression. And finally, if I have evaluated this expression, then I can try to see whether my evaluated expression matches what I just measured, right? So this is what I just measured. And I can evaluate that expression and see if it matches or not. So in here, what I have done is, let's see. So this is the plot where, so I wanted this to be as an exercise, but it looks like things are not working. So I'll just walk you through and hopefully you can work it out later. I will also give you the solution. And if you do work these out, it will be a lot simpler to understand things going forward. So in here, I'm plotting two things. First is what I measured from the initial thing. And second is when I evaluate this expression, which is just behind this red point because they're on top of each other. So they perfectly match each other. So it means what I've just predicted, the expression I showed you, is what we are measuring. So our numerical analysis and analytical expression makes sense. So for any random distribution of point, if it's in a periodic box, then you know how to calculate it. You don't even have to calculate the pair count. You can predict the pair count. This is how it will look like. It's basically a growing function as a function of distance, which is saying nothing, but it's when you go to larger and larger distance, the volume of this shell is going to be bigger and bigger. And so you're going to find more and more points because it's uniformly distributed, right? So the density is uniform. So this was supposed to be second exercise, but with the interest of time, I will just let you do it later, and I will post the solution on the. Okay, somebody else also completed the first one. That's great, Srijit. Yeah, that's perfectly what we expect. So this is what you need to do to find out analytical expression, evaluate the analytical expression for a random distribution of pair count. Now, the other thing you did was calculated the pair count for a cubic grid, right? So can we also evaluate what should the cubic grid look like if you just by looking at this structure rather than doing the pair count for it? So if you look at the cubic grid, there is very grid-like structure. So in the sense that this is plotted a part of a cubic grid, and you'll have a cell size. So if you look at any distance which is smaller than the side length of this, you'll never find a pair point which is smaller than the side length, right? So for any distance smaller than your smaller side length, you'll basically find 0 number of pairs. But when you go to this side length, you'll find a lot of pairs at that length. And any integral multiple of the side length, you'll find a lot of pair. But anything in between, you'll find 0 point, right? So that's fundamental mode of the cube. It's essentially just the side length of the cube. So what you expect when you do pair count, you'll expect to find a delta function around that place. But then there will be higher order mode, right? So you can also find this diagonal. You can find a lot of points which are at the phase diagonal. So they will be separated by square root of 2a. And all the higher order mode of that. So all the integral multiple of that. And then you can also find a 3D mode, which is looking at the main diagonal of the cube, which is square root of 3a. So you'll find a lot of pair at square root of 3, and then all the higher order mode of it, right? But then if you try to generalize it, even more general, it's a very interesting theorem in mathematics. You can basically take any number of side length in x-axis and any number of side length on y-axis, square them and sum them. That will form your phase diagonal, some or other form. So any number which is sum of a square of two numbers, so this is called two-square theorem, should be a fundamental mode of a cube, right? Similarly, for the 3D, like the main diagonal axis, you can take any 3 integer and square it and sum it, for example, this one, and you'll always find a pair corresponding to that mode. So any number which is sum of 3 integers, square of 3 integers, you'll always find a fundamental mode of the cube. So if you use the 2-square theorem and 3-square theorem, you basically have all the fundamental of cube. So A, all the integer multiple of A, anything which is sum of a square of 2 and sum of a square of 3. It's a very interesting proof for 3-square theorem. You should read it on Wikipedia. I actually provided the link. It's a very small and very interesting proof if you like this sort of tricky proof. I've provided some details about it, and then I've written 2 functions just to compute this. And this is also to get you some sense of like some decisions when we will make, which I will come to later. How do you make this decision? If you know the structure of what you're looking at, you can make this decision much more easily. So if you just execute these functions, then what this plot is all the fundamental mode of cube as a function of distance, given a certain like side length. Once you know the A, you can plot all the fundamental mode of cube. And you can see it's color-coded in the sense that the first, all the side mode is magenta, all the cyan is all the phase diagonal mode, which is sum of 2 square, and all the yellow are the sum of 3 squares, right? And if I go back and look at how my pair count look like compared to how the fundamental modes look like, I don't really see a one-to-one correspondence. So they don't really correspond to each other. If I just told you what I just told you, that I should not find any point which is basically less than this, and I should, or anything in between these two. I should only find where at this scale and at this scale and at this scale, and all of the thing in between should be 0, right? But this is not what this numerical function is showing us when we plotted it. So there's some problem. And what is the problem? If you understand the idea of the mode, then why our numerical results are not matching our fundamental mode or expectation, which did for the random distribution. So for the random distribution, our analytical expression perfectly match with the numerical cons. So this was actually work 3 to actually just make the plots which you have already calculated, and I have worked out. I will put up a tutorial with all the solutions so that you can go through it in more detail, but I'm just trying to make sure I walk you through some of the important stuffs. So it doesn't match. What is the problem? The problem is that something I never talked about is a decision you have to make. So everything is gridded, right? Everything is binary. We don't have a continuous system. Everything is digital in the sense that there are levels. So when I calculate things, pair count as a function of distance, you have to decide, okay, what is the minimum distance, what is the maximum distance, what is the bin size, how many such bins I need to make, and all those decisions needs to be made when you're calculating correlation function. In my cube example, this pair separation, there are very concrete points where I will find pairs. But my bin widths are much larger. So essentially my bin widths are so big that in this bin I will find largely this point, but in between, in this bin will extend to this versus also that, especially at large distances. So you still see these oscillations like the bin center, which is coinciding with that. You see higher value and lower value, but you are kind of averaging the things out. You're smoothing the things out by not having enough bins. And that's what you're seeing, which is why this doesn't match. So the solution is you have to create bins which are much smaller than what you're using now. And if you create bins much smaller, then you'll see this thing will match better. So the reason I gave this example is often you'll have to make decision when you'll go and measure correlation function, what should be my minimum and maximum scale, how many bins should I create linear bin, logarithmic bin? And these questions, the answer to this question will depend on your problem. What are you interested in? And there's no universal thing. Like if I'm studying BEO, I will have very different choice compared to if I'm doing small scale clustering. If I'm studying Halo model, I will make very different choice. So it's important to realize that, okay, these are important decisions and not just use whatever is used in a paper you have read or the default values. And all of these things you can actually set in the pair count function, which I skipped initially to avoid too much jargon. So for example, there is a value called R limit, which essentially tells you what is the minimum and maximum value you want to measure your correlation function, which is 0 and 0.3, which is why if you'll notice all the plots have a x-axis between 0 and 0.3. There's also a variable called n bins, which is how many bins you want between them. And this is all done linearly, right? So what it's doing right now is 0 to 0.3 and 20 bins. So it's creating 0 to 0.3, 20 bins. And that's not enough. So if I want to match it, then what should I change in my function call? What should I change to actually get more reasonable, to actually see these modes in the cube, in this function call? Sorry? Right. So I should just make more bins so that each bin is much more smaller, and so you're not smoothing, you're smoothing fewer number of points, right? So let's say if I make that bin, so this was my next question exercise, which you can try to do later. But let's say I just do the exactly same thing what I have done, but I will just change the n bins to something like 200, right? If I will change the n bins to something like 200, I will get a plot something like this. So now again, the vertical lines are the fundamental modes of the cube, and all the blue dashed line is what I measure. So you can see they're perfectly corresponding to these modes. And the red point is the random distribution, what it looks like for the random distribution. So just by making whether I will choose the right binning or not, I can see an effect or not. Right? I can smooth the effect. I can miss out things if I don't use the right binning for my kind of science case. So it's always important to think about what you're looking at, what kind of structure you want to find, and then decide this binning. So this is essentially gives you most of the idea of what really pair count is and what it involves. Whenever you do pair count, this is really one of the main things, what kind of binning you want to do. Okay, and this is all in 3D. So now, but this is not correlation function, this is just pair count, because the way I define correlation function is it's the excess probability of finding a pair of points as a function of distance compared to random distribution. So I want to compare that with the random distribution, and I want to find only the excess. So you can say, okay, how many number of points DD, so D is, let's say, your data, which is points in the grid, and RR, which is number of points you find in the random, and DD over RR is the number of points you find in the data compared to number of points you find in the random in the same volume, right? And if I subtract -1, so if my DD, the cube I'm looking at, is actually random distribution, then DD and RR is going to be same, so that's going to be always 1. If I subtract -1, it's 0. So for a random distribution, correlation function is going to be flat, 0, right? And what you're going to see, if there is a pair, like in my field, if I have more than random distribution, there are regions where you have more pairs at certain scale, then this will be positive. If it's less than random distribution, then it's going to be negative, right? So this is the basic definition of correlation function, but there are other estimators. So this is called estimator. This is one of the estimator which is most simple to understand, but there are other estimator, and the reason you use different estimators is because they have different noise probability typically. And they have also some advantage with the systematic. A popular estimator is called Landis-L estimator, which is you calculate the same thing, DD, but you also calculate the cross pair, -2dr plus RR by RR, right? And the nice property about Landis-L is shown to be minimum variance estimator, which means the noise in your measurement is going to be minimum when you use this estimator for clustering measurement. But this is not always possible to use. For our purpose, you can always stick to this unless we are really doing precision cosmology, where we are worried about the characteristic of noise and we are worried about the precision of the parameter, right? So you can use either of those two. You understand the idea of pair count. So once you do the pair count, you always have to have a random distribution to compare with. Yeah, okay, so that's perfect. We are almost done. You always have to have random distribution to compare with. So whatever your galaxy catalog, let's say in cosmology, you're going to essentially do the same exercise, find the number of pair of galaxy as a function of distance. You have to make choices of the binning. And then you throw random distribution, you create a random field, and again do the pair count for the random, and compute this. This is what your correlation function will look like. So if I'll do that, then, so this was the case when it's just the pair count. If I do that, then this is how it will look like for the correlation function. So this is the correlation function for a cubic grid, where the blue dashed line is the measurement, and the vertical bound is the fundamental cube, which is essentially my prediction, right? And they perfectly match in terms of the mode. But then I can also make a statement about the height of these things. If you really think about how many modes are there in the cube per unit volume, you can say, okay, these two should have basically the same height, and this should be 1/3 of that height. I'm not going to go in detail, but you can actually very easily work out, and you should try. That is one of the exercises, that the first two modes should be same height, and the third mode should be 1/3 of the first two mode. How do you calculate that? And this nice feature is because you're comparing with the random. So there are a lot of nice feature comes in because of that. Also, you can see the plateau is -1. The minimum value is -1. This is because in the cube, other than these fundamental modes, everywhere else you have 0 pair count. But in the random distribution, you'll have some pair count, right? But given that cube is 0, so you are making the whole ratio 0, and you're subtracting 1 -1. So these regions, compared to random distribution, are actually very underdense, right? So you have in much few, even basically zero pair of objects in your cube compared to random distribution. And wherever you have fundamental mode, you have lots of points. So the absolute height is not that relevant. That depends on the grading you have. But the ratio of the height is something you can actually work out. And you should try to work out. This was essentially the last thing I wanted to cover today in terms of correlation function. I'm sorry things didn't work out. I will try to think of a better way how to do. Maybe we will try to install things on everyone's laptop before the next session. But I hope you got the idea of correlation function and what are the things you need to worry about, like the first set of things when you measure correlation function. And there's going to be a notebook with solutions available on the same link. So it will be tutorial 1 solution. You can go over it in detail. And if you have any questions or if you didn't understand anything, feel free to ask me. So I'll stop here. And if you have any burning question, we can take it now or we can discuss later offline. Also, feel free to ask questions on the Slack, so that not me, other people can see it, the solution, question and answer both. Any burning question? All right. Yes, yeah, so please also, if you think you know the answer to any question, please respond. That's the whole idea. We want to learn, all of us should learn together, so everyone is going to teach as well as learn. So whatever you know, please share with everyone.